In this video, I'll go through some examples that work with compound interest, which is an application of the exponential functions that we considered in a previous video. So there we had f of x equals a times b to the power x, which we could also express as a times 1 plus r to the power x. And here a is the initial value when x equals 0, which in the context of compound interest is given the name the principal, and then r is the rate of increase or decrease as a decimal, and in the context of compound interest problems we're often given an interest rate as an annual interest rate, and then to find the value of r in this formula we need to divide that annual interest rate by the number of compounding periods per year. So we'll see exactly how that works in the examples that we're going to consider. The argument of the function x in the context of compound interest, this represents the number of compounding periods. And so often we're looking at, say, finding the value of an account a certain number of years in the future, and if interest is compounded monthly, then we need to multiply the number of years that we're talking about by the number of compounding periods per year, so 12 in that example. So again, we'll see exactly how that plays out in the two examples that we're going to consider. So first of all, let's think about a savings example where we're initially investing $2,000 and our annual percentage rate, APR, so our annual interest rate is 3%, and we're compounding interest monthly, and we want to find the account value in 4 years. So the first thing to do is to figure out what R is in our formula. So R is the interesting rate per compounding period. So we need to take that annual interest rate and divide it by 12 because we've got 12 months in a year. So let's do that first. So R is going to be equal to, and we need to express the interest rate as a decimal, not as a percentage. So 3% will be 0.03, and then we need to divide by 12. So we're going to have 0.0025 for the value of r. And so now we can write down our exponential formula, and a is 2,000, that's our initial investment, and then we have 1 plus r, so 1.0025, and then to the power of x. And if we're trying to find the account value in 4 years, then remember x measures the number of compounding periods, so we need to multiply 4 by 12 in this case. So we're trying to find f of 4 times 12 is 48, so f at a value of x equal to 48. So write out our formula again, and this time we can write in 48 for x, and then if we evaluate that on a calculator we get $2,254.66. So that's how much the account would be worth after 4 years if we initially invest $2,000 and the annual percentage rate is 3% and we're compounding the interest monthly. Let's do another type of example. So this is a different kind of example where we have a savings goal of $5,000 in 10 years, and the annual percentage rate in this case is 6%, and it's compounded quarterly, and we want to find out the principal. So how much would we have to invest at the beginning to have $5,000 in 10 years time? Okay, so first step in a compound interest problem is figure out what R is. So 6% is the APR, the annual percentage rate, and we need to divide by the number of compounding periods in a year. So we're compounding interest quarterly in this problem, so we need to divide by 4. So that's going to be 0.015. And then let's write down our exponential function. So we don't know what a is yet. A is what we're trying to find out. So I'll just write a for now. And then we've got 1 plus r, so 1.015, and then x. And x represents the number of compounding periods. So our goal, our savings goal, is 10 years time. So the number of compounding periods is going to be the number of years times the number of compounding periods per year. So x is going to be 10 times, we're compounding quarterly, so 10 times 4, so 40. So we could write down that f of 40 equals a 1.015 to the power of 40. But we know what the value of the savings account should be in 10 years time. We want it to be $5,000. That's our savings goal. So we can set that equal to 5,000. So now we have an equation with one unknown, a, and that's what we're trying to find out. That represents the principal, the initial investment. And so we need to solve this equation for a. So let's do that. So a is going to be equal to, if we divide both sides by 1.015 to the power 40, we'll have a isolated on one side, and we'll have 5,000 over 1.015 to the 40 in the denominator. And if we evaluate that on a calculator, we get $2,756.31. And it's a good idea to check our answer here. And it's an easy check, because all we need to do is use $2,756.31 as our value of a, and see if we get the answer 5,000 if we plug that into our exponential formula. So let's do 2,756.31 times 1.015 to the 40, and evaluate that on the calculator, and sure enough it comes to 5,000. So that's a couple of examples of compound interest problems.